In this lecture, we're going to talk about head losses in pipe flows. In the previous lecture, we talked about the extended Bernoulli equation, and in that equation, we had this term called the head loss term. And it's the term where we take into account viscous losses in pipe flow. So we're going to talk about how we actually calculate those viscous losses, or that head loss, in that extended Bernoulli equation. So that's what we're going to talk about today. Go ahead and take a look at your screen. The picture I have on here is of the Trans-Alaska Pipeline. It's Alaskan pipeline. It goes 800 miles with the 4-foot diameter pipe. You can see the pipe, going all this distance. It's actually raised off the ground, and every now and then you can sort of see right in here these, they're actually radiators sticking up on, let's see if we can zoom in on that. There are little radiators that actually stick up off the pipeline to help dissipate some heat that's generated as the oil flows through that pipeline. It's a very impressive engineering project. And obviously a pipe flow, which is what we're interested in for today's lecture. So let's go ahead and get into the material. So just a reminder from last time, in the last lecture, we talked about the extended Bernoulli equation, which is this equation here. Looks just like Bernoulli's equation, but there are a few extra terms here. We have this alpha term, which is the kinetic energy correction factor. And the reason we have that is because we're using an average velocity in the flow through the pipe here. We're assuming a real pipe flow with a velocity profile. So we're going to use the average velocity, but we want to make sure we have the same kinetic energy as the real profile. So we have this correction factor that makes sure that we have the same kinetic energy. And so flow through a circular pipe, if it's laminar, that correction factor comes out to be a value of 2. So the transition between laminar and turbulent flow in a circular pipe flow occurs at a Reynolds number of about 2300. So if the Reynolds number based on the pipe diameter, let me actually write that down. So the Reynolds number based on the diameter would be the average velocity in the pipe times the pipe diameter divided by the kinematic viscosity of the fluid. And so if that Reynolds number is less than 2300, then it's laminar. If it's greater than 2300, then it'll be turbulent. In reality, there's a transition region, but we'll just treat it as being turbulent. And in that case, the value for the kinetic energy correction factor that we'll use is equal to 1. And the reason for that is because the velocity profile for a turbulent flow looks a lot closer to an average profile because it's been mixed and it's more uniform and more blunt shaped, and so it looks like an average velocity profile, and that's why we get closer and closer to a value of 1 as the flow becomes more and more turbulent. So getting back to the extended Bernoulli equation, we have this kinetic energy correction factor, so that's one difference from the regular Bernoulli equation. Then we have this head loss term, which is where we're going to focus our efforts today. And then we have the shaft head term. The shaft head term is there to take into account any pumps or turbines, compressors, fans, any kind of rotating shaft kind of machinery. We'll deal primarily with pumps in this course, or a turbine. It's there to either add energy into the flow or take energy away. And that shaft head term is related to the power, shaft power, through this relation here. This is the shaft power. In fact, I should change other to let's just call it shaft. The shaft power acting on the fluid, and so if it's a pump, it's adding energy in, and the power should be positive. You divide through by the mass flow rate and the acceleration due to gravity, and that gives you the shaft head term. If it's a turbine, then W dot would be negative because you're extracting energy away, and then the shaft head term would be negative in that case. So the extended Bernoulli equation really is a statement of the first law. We have some energy coming in, so here you see a kinetic energy type term, a potential energy type term. This is a pressure work type term, it has the same units as energy. So the total energy coming in, we subtract some energy because of losses. These are due to viscous losses. Perhaps we add energy in if there's a pump, or we subtract it out if it's a turbine. And then this is the energy you get out. Okay, so that's that equation. But we're going to really focus our efforts right now on this head loss term right here. We want to determine how we evaluate that term. So to get started on that, we're gonna actually go back to the Navi Stokes equations for viscous Newtonian flow through a circular pipe. And in particular, we'll look at steady, laminar, Newtonian fluid flow through a pipe. Pipe will have a radius r. We're going to make a number of assumptions, just like we did back in the Navier-Stokes equations. In fact, I did this exact problem in an example video back in the Navier-Stokes section of the course. I'm just going to recap it here. I'm not going to go through all the details. But what we did is we assumed that we were dealing with a steady flow, fully developed flow in the z direction, so the velocity profile doesn't change in that z direction. We're not going to worry about gravity, and it'll be axisymmetric with no swirl component. If we make those assumptions and analyze the continuity equation in cylindrical coordinates, you'll find that there should be no radial velocity. So from this, you'll end up getting that UR is 0. And then with that information and those assumptions, we go to the Navier-Stokes equation in the z direction, which is this one. And we can simplify a lot of terms here. In fact, let's go ahead and quickly do that. We have steady flow, so that's because of number 1. This one is 0 because of, let's call this number 5 here. 0 because of number 5. This one is 0 because of number 4. This one is 0 because of number 2. What's driving this flow is a pressure gradient in the z direction, so we'll keep that one in there. That's what's pushing the fluid through the pipe. This one is 0 because of number 4. This one is 0 because of number 2. And then the last one is 0 because of number 3. So what you have is just these two terms that I've underlined remaining. Then we can go ahead and solve that differential equation that results. And we need to solve it with respect to, we need to apply some boundary conditions. One boundary condition is there's no slip at the pipe circumference. That just means that the uz velocity at r is equal to capital R should be 0. And then the other boundary condition, because there'll be two unknowns when we solve the second order differential equation. The second boundary condition is that the flow velocity remains finite. That just means that the uz can't go off to infinity, has to remain finite. Okay. In particular, when you solve the differential equation, there'll be a natural log term. And the natural log, as the radius goes to 0, goes to minus infinity, so that term has to disappear for the flow to remain finite. When all is said and done, you get this expression right here. This is the velocity in the axial direction as a function of radius, and you see it's a parabola. It's kind of a paraboloid relation. Again, this should all be just a refresher. You should have seen this before. And this solution is specifically valid if the Reynolds number based on the pipe diameter and the average velocity in the pipe is less than 2300. 2300 is just an engineering rule of thumb based on experimental data. Okay. From that velocity profile, we can get the average velocity just by saying that the volumetric flow rate using the average velocity, which would be u bar times pi r squared, is equal to the volumetric flow rate using the real velocity profile, which would just be the integral of this real profile integrated over the area as r goes from 0 to capital R. And when you do that, you'll find that the average velocity is equal to 1/2 the maximum velocity. And in terms of the other variables, when you plug this in to here, you'll get it equal to that, where the diameter is just, of course, 2 times the radius. I just put it in terms of diameter there because we'll use diameter later in the derivation. All right, some other things that are useful to know are the wall shear stress, just tau W. That'll just be mu times du dr evaluated at the wall. And using this profile, you can substitute that in here and you'll get this expression. And I'm going to express it in terms of the average velocity that we just solved for right up here. So I substitute that in and we get this. Unfortunately, I switched back to radius. I'm not quite sure why I did that, but here it is in terms of radius. And then since we like to make things dimensionless, we'll express that wall shear stress in a dimensionless form. And that's what we call the friction factor, or in this case, it's actually known as a Darcy friction factor, but a lot of times people don't say the word Darcy. The reason it's a Darcy friction factor is there's another friction factor when you deal with compressible flows called a fanning friction factor, and but we're not going to cover that in this course, so it's fine to say friction factor. So the friction factor is just 4 times the wall shear stress made dimensionless by the dynamic pressure of the flow. The number 4 in there is just historical. Just leave it in there. And if you express the wall shear stress in dimensionless form, it ends up looking like 64 over the Reynolds number. That's an important relation that we're going to come back to in just a little bit. So the friction factor is just a dimensionless wall shear stress. Now, I'm telling you all of this stuff, we're going back through this because I'm ultimately trying to get back to the head loss term. And remember that the head loss term is related to energy losses due to viscous effects. It's really the term is why we have to have a pressure gradient. Like in this particular flow, we have this pressure gradient. Let me just go back to the picture. There's a pressure gradient here. There's a dp/dz that is less than 0. The idea here is that you have to push on this side with more pressure than over on this side so that you can push the fluid from left to right. And you have to apply that pressure because you're overcoming the viscous effects, right? There's no slip at the pipe walls, and so if you didn't push on the fluid would just come to rest eventually, right? So you have to keep pushing it to overcome those viscous effects. If it was inviscid, so if there were no viscous effects, I could just tap on one side of the fluid and it would just keep propagating through the pipe. Nothing would slow it down. But because it's viscous, we have to constantly keep pushing on it. And so we have to apply some pressure on that side, a little extra pressure, delta P, so that we can push the fluid along. And the pressure gradient, since it's a fully developed flow, well, it'll be a constant. So the pressure gradient here, dp/dz, let me just write it as an ordinary derivative, will be like delta P over L. It's just the change in pressure over the change in distance. Here I've just said the distance is L. Okay, so that would be like our pressure gradient here. And so we're going through this because I'm gonna relate some quantities to that pressure gradient and ultimately relate it back to the head loss. Okay, so all of this is just a recap from the Navi-Stokes solution for laminar flow through the circular pipe. Okay, so now let's start getting into some new material. So I'm going to revisit this average velocity equation because I've got it in terms of this pressure gradient. Let me rewrite that pressure gradient dp/dz back in terms of the delta P over L. Okay, so that's what I'm going to do next. That's right down here. I've just rewritten this. Let me just show it. I've just rewritten this expression right down here, and I've just used, instead of dp/dz, I did delta P over L. And I'm going to put absolute value on here. I just want the magnitude of these things. I'm not going to worry about the sign. And then I'll rearrange this to put the change in pressure. This delta P is how much extra I have to push on one side to get the fluid to go through there at velocity u bar. So how much extra pressure do I have to apply to get the flow to go at this average velocity? So I'm going to express the pressure in dimensionless form. So here's the extra pressure I have to apply, divided by the dynamic pressure based on the average velocity. And if I just rearrange this equation, it'll look like this. So this is just rearranging the equation. And what you'll see here is, let me just rewrite that one other way here. What you see is that you get this grouping of terms, rho, u bar d, all over mu. Well, we know that that's like 1 over the Reynolds number. Okay? So we could rewrite this equation then as the little extra pressure that we have to apply to get the fluid to move through the pipe, expressed in dimensionless form, is equal to 64 over the Reynolds number times L over D. L over D is just kind of the aspect ratio of the pipe. It's the length of the pipe divided by the pipe diameter. So this 64 over the Reynolds number naturally shows up in the derivation. Remember that 64 over the Reynolds number is this friction factor. So we could rewrite that pressure drop in terms of the friction factor. The extra pressure that we have to apply to the pipe is directly related to the wall shear stress, tau W, which it's not entirely surprising. So we rewrite this extra pressure term, we call that term a loss coefficient. It's a pressure loss coefficient. And the symbol that's often given to that is a K. So K is our loss coefficient. It's the pressure loss coefficient. It's how much extra pressure we have to apply to overcome those viscous forces. Okay, so that's what that is. And so for this viscous pipe flow through this, this laminar viscous pipe flow, our loss coefficient, K, is just the friction factor times L over D. Now I put here K major because it turns out we have different kinds of losses that we're going to deal with. We have losses due to the viscous effects of flow through just a straight section of pipe, and we call those major losses. Let me write this down. A major loss is let me write viscous loss in a straight section of pipe. And then we'll have what are called minor losses. And these are viscous losses due to, or I should say, they're in other things like valves and bends and tees and things, other things that you find in the pipe system. So I'll say in valves, elbows, contractions, etc. So anything that's not a straight section of pipe. Okay, and we'll come back to that in just a little bit. So we just break up those losses into two parts. We have losses due to viscous effects in a straight section of pipe, and losses due to viscous effects in like pipe bends. A contraction is just where the pipe just suddenly expands. Where the pipe suddenly contracts. An expansion is where the pipe suddenly expands. Tees, where the fluid goes and breaks into two parts. Things like that. Those are all called minor losses. You have to apply extra pressure to push fluid through those like a valve, because in the valve there's some complex fluid motion, and anytime the fluid has some velocity gradient, of course you have shear stresses, so you have to apply a little extra pressure to overcome those shear stresses. And we express that extra pressure that we have to apply in terms of this loss coefficient. Okay, so specifically for these major losses, it's a friction factor times L over D. That's how we express it. And specifically for a laminar flow, let me write it differently. So the friction factor for a laminar flow, we just derived a little bit ago, is just 64 over the Reynolds number. Now, if it's a turbulent flow, it's a different value. So that's really important. Make sure you make a note of that. Is the friction factor for laminar flow is 64 over the Reynolds number. We just derived that. But if you're dealing with a turbulent flow, it's actually a different value. We don't have a Navi Stokes solution for that one. Instead, we actually rely to some degree. There's some analysis we can do, but we rely to a large degree on experimental data. Okay, and I'll show you that in just a moment. So it's important to remember this, what the loss coefficient is, and that the major loss is just friction factor times L over D, and that specifically for a laminar flow, the friction factor is 64 over the Reynolds number. So I'll tell you in just a moment how we deal with minor losses and how we deal with the turbulent major loss. Okay. Before we go further, let me just go back to the extended Bernoulli equation and just let me show you how this kind of, where this loss coefficient appears. Let's imagine we're dealing with a straight section of pipe so that there's no change in elevation. We'll say, the pressure over here is P plus delta P. The pressure here is P. The distance is L. Diameter is D. And we're trying to find and it's a constant diameter of the pipe. And let's just go ahead and evaluate the extended Bernoulli equation as we go from point 1, or let me just call it in and out. So this is in, and over here will be out. So when we evaluate the extended Bernoulli equation, the velocity in and the velocity out will be the same, just from conservation of mass. It's the same cross-sectional area. We're assuming incompressible fluid. So those terms drop out. We don't even need to worry about what the kinetic energy correction factor is. I'm going to assume that it stays laminar or it stays turbulent. We'll just assume it's laminar flow in this case. So we don't have to worry about that. Same average velocity, same kinetic energy correction factor, same elevation, so those go away. There is no pump or turbine, so there is no HS term. So then what we'll get is our head loss term, if I just rearrange this, will be equal to P in minus P out all over rho G. This will just be, if you look at this, P in has an extra delta P, right? It's just the P in minus P out will just be delta P over rho G. So our head loss, you can see, is just related to the change in pressure that we have for this particular case, right? And I could rewrite that change in pressure in terms of my loss coefficient up here at the top. And I can do that if I substitute that in. This will be K times 1/2 rho V bar squared. That's the delta P all over rho G. And then so then it'll end up becoming K times V bar squared all over 2G. So you can see our loss coefficient and our head loss. So here's our head loss term is related to our loss coefficient times V. This is kind of our velocity head term. This is the velocity where that loss occurs. So I wanted to just show you the connection between the head loss and the loss coefficient. So we can express all of our head loss terms, whether it's a major loss. In this case, I was just showing you a major loss, but we can express all of our losses in the same form, just like what we have on the screen here. So we can do major losses and minor losses in that manner. And if we do that, then our head loss term, just in general, will be the sum of, let me just double check, I don't think I have it elsewhere. So it's the sum of all the loss coefficients times the velocity heads where those losses occur. So this is for all losses. This symbol here, this kind of V shape with a bar through it, that's not a volume, that means for all. It's a mathematical symbol just saying for all. So for all the different loss mechanisms, major losses and minor losses, the total head loss will be the loss coefficient corresponding to that loss. So it could be a major loss, it could be a minor loss, times the velocity head where that loss is occurring. Okay, so what I mean by that is, let's say we have the following kind of situation. Let's say we have a valve, and then there's kind of a bigger diameter pipe. So this is D1, this is D2, and we'll say that this is some sort of valve right there, and the flow is going this way. When I calculate what my head loss is as I go from, let's say, this point A to point B, the total head loss in that case, I'm just going to go back to my equation here, okay? And then my total head loss would be the loss in this pipe. That's a major loss, so I'll call that K1, or K1, I'll just make a note major here. Let me rewrite that because that looked terrible the way I wrote it. So K1 major times the head loss, or times the velocity head where that occurs. So I'll call the velocity in that pipe, call it V1 bar. So that'll be times V1 bar squared all over 2G. I have another major loss. Let me highlight this one so I can show which part these correspond to. I have another major loss occurring in this pipe. Let's call the velocity in that pipe V2. So V bar 2. So the loss there will be K2 major, because it's a major loss. It's just a loss in a straight section of pipe, times the velocity head where that loss occurs. But that's a different velocity because it's a different diameter. So we'll call it V bar 2 squared. So that one's going to be in green. And then I have one additional loss here, which I'll highlight in kind of this pink color, and that's the loss where the valve is. That's a minor loss. So we'll just call this valve minor, just to indicate that it's a minor loss. And the velocity that we'll use for that one, so the way we find out what that the loss coefficient is for that valve is we typically look it up in a table. And when you put those values in a table, they tell you what velocity to use. Now for a valve, it's typically going to be the velocity just upstream of the valve. So in that case, the velocity head there would be V1 bar squared all over 2G. So that's that one. So as we go from point A to point B using our extended Bernoulli equation, our total head loss in this particular case would be a major loss in the first pipe, a major loss in the second pipe. And again, those are losses due to viscous effects in a straight pipe. And then we would also have this minor loss due to the valve. And that's because of the viscous effects and all the like turns and movement of the fluid through the interior of the valve. And again, because there's some velocity gradients in there, you get viscous effects. That dissipates energy, and so you need a little extra pressure to push through that valve. And that's this one. And the way we would find that loss coefficient for the valve is we would go to a table, which I'll talk about in a moment. Okay, so this is a very important relation to remember as well, that the head loss is just the sum of all the losses which are found by total head loss is the sum of all the head losses through the whole inlet to outlet, and those individual losses are found by taking a loss coefficient times the velocity head where that loss occurs. And if you're dealing with major losses, it's found using this expression here. If it happens to be a laminar flow, then you can use that. If it's turbulent, we'll deal with that in just a moment. If it's a minor loss, then your K value you would have to find from a table, which we'll talk about in a moment as well. So let's go ahead and talk about how we deal with turbulent pipe flows. Okay. So for that case, I mentioned just a moment ago, what we actually do is we rely on primarily experimental data. Okay. So the laminar flow, we can go back to the Navi Stokes equations, get an analytical expression, which we did. 64 of the Reynolds number was the friction factor. When you're trying to find the friction factor for a turbulent flow, we just do a lot of experiments and then tabulate the data and present it in a plot. And that plot shown here is known as a Moody plot, or a Moody diagram. Okay, so this is what's called a Moody plot, and this allows you to find the friction factor, which is right over here. This is that Darcy friction factor, as a function of the flow Reynolds number. So this is the Reynolds number based on the average velocity in the pipe and the pipe diameter. Okay, and then over on this side, we have what's called the relative roughness of the pipe. And I'll talk about that in a moment. So let's not worry about the relative roughness for a moment. Okay, so we have friction factor versus, let me shrink this down, versus Reynolds number. Now we know already that when you're dealing with a laminar flow, the friction factor should be 64 of the Reynolds number. Laminar flows for these circular pipe flows occur for a Reynolds number less than 2300. So going down to the plot here, 2300 is right about, there's 2000, so I don't know, it's probably right about in there. So if I come up here on the Reynolds number, so this is about 2300. So on this side, we have laminar flow. And this line here is actually equal to 64 over the Reynolds number. So the way we use this Moody plot is we'll come over here and say, let's calculate the Reynolds number. Let's say it's 1,000. So it's a laminar flow. We come here to 1,000. We come up until we hit the line. Let me actually draw the line. So we come up from 1,000 till we hit the line here, and then you come over to the left and you read off the friction factor, and it would be close to 0.07. So that's how you can use the Moody plot. So if you can't remember 64 over the Reynolds number, but you have the Moody plot, you can still find the friction factor for the laminar flow regime by just using this line. If it's turbulent, then it turns out that the roughness of the pipe actually plays a role. So what I mean by that is this. Let me sketch something out up at the top here. Let's say we have our pipe. Now, pipes typically have some asperities on it, just little bumps on the surface. So these bumps, the bumps on the surface actually affect the turbulence in the pipe. It has to do with the fact that you've got these small little vortices near the pipe walls, And the size of the bumps affect the size of those vortices, and thus affects the overall wall friction, shear stress or wall friction. So the relative roughness is kind of a measure of the roughness, epsilon, to the diameter of the pipe. It's just a dimensionless roughness. So epsilon is just a measure of the roughness of the walls, and so the relative roughness is given over here on the right-hand side. The way you find the roughness for different kinds of pipes, it's been tabulated, and I'll show you that table in just a moment. Okay, but for now, let's just say we're dealing with a turbulent flow, and we have some relative roughness that we've looked up in a table. The way we find the friction factor for a turbulent flow would be this. We would calculate what the Reynolds number is. Let's say it is, let's say it's 10,000. Okay, so 10,000 is right here. What we would do, and let's say, so our Reynolds number is 10,000, and let's say our relative roughness is 0.002, right there. Okay, so that again is a measure of the roughness of our pipe walls. So the way this works is we go up here on the Reynolds number axis, and then we also come over on the relative roughness line. We just follow that, and you'll see that it curves upward. We see where those two intersect, and then we come over horizontally and read off the friction factor. So the friction factor in that case would be like, I don't know, 0.035, something like that. Okay, so that's how you use the Moody chart for turbulent flows. So it depends on, for a turbulent flow, it depends on the Reynolds number and the relative roughness. Now to find the relative roughness, like I said, there are, let's see, do I have it here? Yeah, here we are. There's a table here that gives you the average roughness for commercial pipes. So you have different kinds of material here. Galvanized iron, for example, and you can see what the relative, this is the roughness, this is the epsilon quantity. So the roughness for galvanized iron is 0.0005 feet, or if you want it in millimeters, it's right there. And so the relative roughness would be that value divided by the pipe diameter, whatever that might be. And these are just ballpark values. And you can see that some of these have quite a wide range. You know, concrete, for example, depends on how it's finished. Even galvanized iron, it gives a value here, but it depends on whether it's a new pipe or an old pipe. So these are just ballpark, back of the envelope kinds of numbers, just to get you sort of in the right order of magnitude for your model predictions. There is one in here that's kind of interesting. There's a plastic or glass, so like this would be like PVC pipe, and it says it's smooth, 0. So it's a very smooth surface. Doesn't mean it's frictionless. It just means it's smooth. And so where that curve corresponds, where that shows up on the Moody plot, is this bottom curve here. Let me highlight it for you in yellow. So this is the smooth line. So if you're dealing with a PVC pipe at a Reynolds number of 10,000, you come up to this line right there, right where it intersects the smooth line, and then go over and read the friction factor. Okay? Now there's two other features on this plot that I want to show you. There's another region here called the wholly turbulent zone right up here, or wholly turbulent flow, or fully turbulent zone. You'll hear different names for it. And that's this kind of dashed line here that I'm highlighting in yellow. What that zone is when you're above that curve and to the right, so up in this region, what you see is that our lines are pretty much horizontal in here. Okay, so what that means is that the friction factor is really only a function of the relative roughness. It no longer is a function of the Reynolds number. You can see that since it's a horizontal line, it doesn't really depend on the Reynolds number anymore. That once you get to a large enough Reynolds number, then the Reynolds number doesn't make much of a difference any longer. It's really just the relative roughness that's important. So that's called the wholly turbulent flow. So that region occurs when you have really large Reynolds numbers. Like the Reynolds number in the Alaskan pipeline, I haven't checked it, but it could be in this wholly turbulent flow. I wouldn't be surprised if it was, because it's such a big diameter pipe that the Reynolds number is probably going to be large. And that would put us in this zone where just the relative roughness makes a difference in what kind of friction factor you would have. Right? Hopefully that makes sense to you. by the way, if you're dealing with relative roughnesses that kind of fall in between, let's say you had a relative roughness that was 0.003, you would just, in that case, you would just kind of have to eyeball it the best you can to kind of follow. Oh, that was a terrible line. You just kind of follow it along right in the middle. So some of these things you have to interpolate, just kind of eyeball it. The Moody chart is not meant to be super accurate. It's just to give you estimates. The very last thing, let me erase some stuff here because it's kind of messy. But the very last thing I wanted to show was this transition range. Okay. So you see there's this, this region here. It's called the transition range, right in this region. There, we don't actually have a really good value for the friction factor. And the reason for that is because we're starting to transition from laminar flow into turbulent flow, which is over on this side. Right? So the laminar flow ends at about, let me put this in red, ends at about 2300. And then here we've got, kind of the turbulent stuff occurring closer to a Reynolds number 4000. So in that range in between, what happens is the flow has characteristics of both a laminar flow and a turbulent flow. So it'll be laminar for a while, and then it'll become kind of chaotic and become turbulent looking for a little bit, and then it'll randomly shift back to being laminar, and then shift to being turbulent again. So it's kind of doing both. And so the friction factor actually varies wildly in that range. So the friction factor in that transition range will be somewhere in between these two curves. So it'll be in this yellow zone. So at best, all we can do is just kind of bound the friction factor there, that it could be somewhere between, if we're at a Reynolds number of 3000, 3000 would be, I'm not sure exactly where it would be, but it's somewhere right in here. It would either be between that value of 0.025 roughly, and depending on the relative roughness, it could be all the way up to this value of about 0.075. So it varies a lot in that transition zone, so we can't get an exact value for it. All we can do is get a range for it because it's so unpredictable in that region. Okay, but fortunately, it's just a narrow region where we're transitioning from laminar to turbulent flow. As engineers, we typically don't like to operate in regions where the behavior is unpredictable. We like to be able to predict what's going to happen so we can prepare for it. When it's unpredictable, that's much harder, and we don't typically like that. So that's the Moody plot, and this is how you would find the friction factor for the major loss coefficient. So again, this F that you would find from this Moody plot would fit in right up here for our major loss. And if it's a laminar flow, you could either use the Moody plot or just stick with this one. And that's only for a Reynolds number less than about 2300. If you're dealing with larger Reynolds numbers and it's turbulent, then to find this F, you'd have to go back to the Moody plot. And from the Moody plot, you see then suddenly the relative roughness comes into play as well. So you'd have to take that into account too to find out what your friction factor is. So the Moody plot, make sure you know how to use that. It's really kind of a ballpark thing. If you want to automate some calculations, it's tough to use a plot. And so people have done curve fits to determine what the friction factor is. So you can see these expressions. There's a Colebrook formula and a Holland formula here. So these are just curve fits to approximate what's in the Moody plot. Okay, so these kind of curve fits can be incorporated into computer programs and such to allow you to calculate the friction factor in an automated way. So there are two of them here. The one on the right, the Holland formula, is an explicit relation. And what I mean by that is you plug in the Reynolds number, you plug in the relative roughness, and it'll spit out the Darcy friction factor. That one's not as accurate as the Colebrook formula. The Colebrook formula, unfortunately, is an implicit function. Implicit meaning that you still have the Reynolds number and the relative roughness, but now the friction factor is on both sides of the equation. You can't just solve by hand what the friction factor is. You actually have to numerically iterate to a solution. Okay, so that takes a couple more steps. When you do that iteration, a smart thing to do is for your first guess in the iteration is to use the Holland formula to get you close to the right answer, and then within 1 or 2 iterations, you can get a more precise value for the friction factor from the Colebrook formula. So if you want to automate things, you're welcome to use these formulas, but definitely know how to use the Moody plot, because during an exam, for example, you'll have to actually look things up on a Moody plot. Okay. So now we've talked about major losses. Let's talk about minor losses. Okay, so I had mentioned before that minor losses are the result of viscous effects in valves and elbows and things like that. And I try to illustrate that here. So here we have a sudden expansion in a pipe. So the flow is going from, in the top here, it's going from left to right. And you have a pipe with kind of a smaller diameter here. I'm only showing half of it. It's symmetric. So a smaller diameter here and then a larger diameter here. And you can see it's a sudden expansion. Now when the fluid goes through that expansion, it can't make a sharp turn. You will not get streamlines that go like this, that follow the corner. The fluid can't do it. It has some inertia. And so that inertia carries it around the corners. And as a result, you get flow separation. It's literally, a boundary layer separation kind of an effect. And so you get a recirculation zone that I've shown right here. Now, in this recirculation zone, the fluid is kind of swirling around, right? And if you think about the velocity gradients, as you cut through here, there are going to be some large velocity gradients, right? Velocity gradient is just how the fluid velocity changes with respect to position, right? That's what a gradient is, how something changes with respect to position. So because you have large velocity gradients, like a du/dy kind of term, because you have large velocity gradients, it means you're going to have large shear stresses occurring in there. And because you have large shear stresses, you're going to dissipate energy. And because you're dissipating energy, it means you have to push on the fluid to push it through that device, because we put some energy into it and then it's getting dissipated by this recirculation zone and viscosity. So that's why you get viscous losses in these other devices. Not only do you get viscous losses in the pipe, but you get viscous losses in like an expansion shown on the screen here. You can also see here in an entrance, the one on the bottom, this is kind of a square-edged entrance. So the fluid is coming in from some region out here, and it's coming in, and you see it can't take that sharp corner, and so it rounds out the corner, and you get a recirculation zone here before it can finally get close back to the wall. So you'll get some viscous losses in this recirculation zone, and so you'll have a loss coefficient associated with that. This one I showed in particular because you'll see that the effective radius of the flow through this entrance is a little bit smaller than the actual radius, right? You see, because of the recirculation zone, the actual radius is a little bit smaller, so that we call this phenomena is called a vena contracta. I just wanted to show it to you because sometimes you'll hear that term. It occurs when you often have it occurs because you have these recirculation zones, and they're more prominent when you have these sharp corners that the fluid has to kind of round out as it comes in through them. So the vena contracta just means that the actual radius or diameter of the pipe is a little bit smaller than, or the effective radius is a little bit smaller than the actual geometric radius. So anyway, hopefully you're convinced that these recirculation zones cause some viscous losses, and that means that we get a pressure loss. So we have to apply a little extra pressure. Let me just show that here. You have to apply a little extra pressure to push the fluid through that device because you're dissipating energy in these recirculation zones and such. And the more complex the flow path, typically the larger the viscous losses and the higher the pressure drop through the device. The pressure drop just means how much the pressure changes from the inlet to the outlet. So to produce loss coefficients for these kinds of devices, we just go straight back to the definition for the loss coefficient, where it's delta P over 1/2 rho velocity squared. And the way you would do this is it's typically done experimentally. You just take your device. Let's say we have a valve, some sort of valve here. We have flow coming in and flow going out. What we would do is we would measure the pressure here. It'd be P plus some delta P. We'd measure the pressure here, or actually, let me just call it P1 and P2. So we'd measure the pressure at both places. We'd measure the average velocity coming into it. And so for a given pressure, we get a certain velocity through the pipe. And then we would plug those values right up into here. Delta P would just be P2 minus P1. And just take the absolute value of that. 1/2 rho V squared. So you just take the measurements of the pressure, measurement of the velocity or flow rate, and make it into an average velocity. And then you have your loss coefficient. You just plug it in, work out the numbers, and then you have a dimensionless loss coefficient that you can plug into a table. And then you can always come back to it later when you need that value for that particular kind of valve. And that's what people have done. And I show an example of a table on your screen here. So this is a table of minor loss coefficients. It just comes from a textbook. Again, these are just ballpark engineering values for different kinds of components. So an elbow, I'll show you some pictures of these things, but different kinds of elbows, what the angle is of the elbow, whether it's 90 degrees or maybe 45 degrees. Flanged or threaded means the following. So here's an elbow, kind of looks like this. There's a 90-degree elbow. If it's flanged, it means that it connects to the pipe like this, that we have these flanges that go off to the side, and then there's some bolts that would hold it together like that. So that would be a flanged elbow. A threaded elbow would be one where it's actually literally threaded. There's some threads on the pipes, on the ends, and then those thread into another pipe. So it's actually screwed into the pipes. So that's the difference between flanged and threaded. So that would be an example of a 90-degree elbow. The long radius versus regular just has to do with the size of the elbow. They don't give any particular numbers here. All I'll say here is that the long radius just means that it's a bigger elbow. You're going to get a smaller loss because the fluid has plenty of time to follow the contours of that elbow. It doesn't have to make a sharp turn. When you have a regular one that's smaller, then the loss coefficients tend to be a little bit higher because it's a sharper turn and the fluid can't quite make the turn. You get a little more recirculation in those regular elbows. 180-degree bend just looks like this, where the flow is turned 180 degrees. T's look like this, where the flow would come in and it could go two different directions. A union just joins two pipes together, so it's something that connects two pipes. Valves, I'll show you pictures of different kinds of valves. I think everybody knows what a valve is, but I'll show you examples of these different kinds of valves. Here you get some very large loss coefficients, and it's because the flow path through a valve is quite complex, and so you get a lot of recirculation and such, and you dissipate a lot of energy. Entrances are just flow coming into or out of let's say a pipe or a container. So like a re-entrant inlet would be this. Let's say we have a big tank, and then we have a pipe. So here's the free surface. A re-entrant inlet is one where the pipe actually sticks into the tank. So you can see it kind of sticks into the tank there. A sharp-edged inlet would just be where it's a 90-degree just a 90-degree bend there. And if it's slightly rounded or well-rounded, it just means that this has been curved a little bit. So let me draw that. So here's one that's rounded. You can see that it's kind of smooth there, so the fluid can follow it more easily. And you can see, again, the more kind of sharp turns that the fluid has to take, the larger the loss coefficient. If it's well-rounded, so it's nice and smooth, you get a much smaller loss coefficient. So if you're trying to save energy, you want to smooth things out as much as possible so you don't get a lot of recirculation zones. An exit is very much the same kind of thing. It's just how fluid goes from a pipe into a large tank. So here it turns out that it doesn't matter what kind of exit you have, whether it's well-rounded or sharp or whatever, the loss coefficient is equal to 1. And the reason for that is because as the flow comes out, regardless of what kind of exit you have, the flow is going to swirl around and completely dissipate when it comes out into that tank. It's just going to, it's going to hit that large body of liquid here and just completely mix together. So it doesn't matter what kind of exit you have, it's just completely, it's going to completely dissipate the energy. And then the last thing that I'll show on this table are sudden contractions and sudden expansions. So the plot on the left is the contraction loss coefficient, and you'll notice that it actually gives you the Kc here. That corresponds to this curve. You see the arrow points to the left side. And then the expansion loss coefficient is this one on the top, where that arrow is pointing to. These are all in terms of the area ratio, so it shows what the area ratio is up here in these plots. So for contraction, the area ratio is A2 over A1, and for expansion, it's A1 over A2. One other thing that you have to pay attention to is what velocity is used. Remember that when we calculate the head loss, it's like the loss coefficient times v bar squared over 2g. This is the loss coefficient, and here's the velocity head. This is the velocity where that loss occurs. So if you'll notice here, for the contraction loss, we use v2. This is the downstream velocity. That's the only well-defined velocity that you have in this system, because if you have an area ratio that goes toward 0, I guess goes toward infinity, is that right? A1. Yeah, goes toward infinity. That would correspond to basically a sharp-edged inlet. So it'd be like if the incoming flow was infinitely large, so A1 would go toward infinity. And then here would be A2. So the only well-defined velocity in that case would be the velocity in pipe 2 right here, V2. There would be no well-defined velocity out here in A1 because it's infinitely large. So that's why V2 is used for the contraction. And then the same idea holds for the expansion. There, the well-defined velocity is V1 because the velocity in the incoming pipe is well-defined. If A2 goes to infinity, then it becomes just an exit. Okay. And in fact, you should see here, when A2 goes to infinity, the area ratio goes to 0. And you should get a loss coefficient of 1. And so here's the expansion, and it does indeed go to 1. Okay. So when you deal with minor losses, you will want to use a table like this one that I have here. This is the one we'll use in this course. There are many other tables, and they can have varying degrees of complexity. Sometimes they're functions of Reynolds numbers. You can see here, valves that are partially open. They can get much more complex, but they're all found experimentally. Typically, you just run that experiment like I described up here, where you plug in a component, measure the pressure difference between the inlet and outlet, measure the average velocity, and then form your loss coefficient, and you put it in a table. All right. I have here, this will be kind of the last thing that we do for today. I just have here some examples of different kinds of valves and different components, just so you can see pictures of them. I won't go through the details of them. But if you want to know a lot more about these, you can find a tremendous amount of information online. So I encourage you to do that. If you're curious if you want to know more about globe valves, this picture kind of shows how it works. You have a handle here that you can turn, and when you turn it, it moves up and down this kind of plug right here that either plugs up or opens up the flow through the pipe. The flow through the pipe would be like in this direction. So this thing would come up or down as you turn the valve, and it kind of opens and closes the area through which the fluid would flow. So if you want to know more about that, just take a look online. You'll see lots of pictures. They have animations and things like that. So those are different valves, and then here's a table showing just many more different kinds of valves. There's huge variety of minor loss kinds of components. All right. Let's see, I think I've covered everything I wanted to find loss coefficients. So now you know how to find major losses due to viscous effects in a straight section of pipe. You know how to use the Moody diagram. You also know how to find minor losses Those you just look up values in a table. One other thing I should mention between major and minor losses is you might think that major losses are always bigger than minor losses because of the name, but that's not the case. If you're dealing with long sections of pipe like the Alaskan pipeline, then indeed the major losses far outweigh the minor losses. Okay, but if you're dealing with a small system where you have lots of valves and bends and with elbows and things like that, then the minor losses could be much bigger than the major losses. So don't let the names fool you. Major and minor don't mean big and small. They're just two different things. Major losses correspond to straight sections of pipe. Minor losses refer to these devices that appear in pipe systems. So I told you how to find these losses and how we would ultimately include them into the extended Bernoulli equation. So let me go back to that. Here we are. So when we go to the extended Bernoulli equation, as I've shown in this equation right here, as you go from your inlet to outlet, you find your head loss using that expression, where your K is, it's either major or minor loss. This is the velocity head where that loss occurs, and I've already told you how to find those losses. So I'm interrupting the video because there were three things that I forgot to mention when I first recorded it. So I want to make sure I address those here. The first is I want to show you some subtleties in where we define our outlet point and how that affects some quantities in the extended Bernoulli equation. The second thing I wanted to talk to you is about equivalent pipe lengths for expressing minor loss coefficients. And then the third thing is related to hydraulic diameters. So let's first talk about the location of the outlet point. So I'm just going to go through a couple of little examples here just to kind of show you some subtleties with that. So let me draw a little picture here on your screen of a pipe system. We're going to say we have one tank, some elevation up here, and it's going to discharge into another tank that's at a lower elevation. And then the height difference between these we'll just call little h. Gravity is pointing downward. And let me apply the extended Bernoulli equation in this system. And the first time through here, I'm just going to put my point 1 there. There's some streamline that'll go this way and then eventually end up on the free surface of the other tank. And then let me write the extended Bernoulli equation for that situation. Okay, so here's our extended Bernoulli equation. And then let me go ahead and just start filling out some terms here. So since we're on the free surface at point 1 and point 2, those will both be at atmospheric pressure. So P1 and P2 are the same. Also, since those are free surfaces and the tanks we're assuming are very large, then the average velocity at 1 and the average velocity at 2 are both pretty close to 0. They're not exactly 0, but they're awfully small, so we can neglect any kinetic energy contribution due to those. We also know that Z1 minus Z2 is going to be equal to little h. That's our elevation head difference. There is no pump or turbine in between points 1 and 2, so there's no shaft head term, so that goes to 0. And then the head loss term, we'll have two losses here. Actually, three losses. We have a minor loss at the entrance, we have a major loss in the pipe, and then we have a minor loss at the exit. So we'll write those down as well. So we have the entrance minor loss, and the V bar P there, that's the velocity in the pipe, because that's the well-defined velocity for where this entrance is. The only well-defined velocity is just downstream of the entrance. So we'll put that, the velocity head corresponding to that is just the velocity in the pipe. Then we have the major loss. I'll just write it as K major. Also dealing with the velocity in the pipe. And then we have an exit loss. And our exit loss, we know we can look up in a table, but you'll find that the exit loss, no matter what kind of exit we have, is going to be equal to 1. And the reason for that is because as the flow comes out of here, it does kind of swirl around completely, and you lose all the kinetic energy that's in that flow. So you have a loss coefficient of 1 ultimately. The entrance loss you could look up in a table and depend on, if it's a square-edged entrance or a smooth entrance, you'll get different minor loss coefficients. But anyway, you can look that up in a table. So if we go ahead and simplify the equation, what we'll get then, let me just think my way through this here. We'll have little h is equal to k entrance plus k major plus k exit times the velocity head. So that's what we'd get in that particular scenario. Okay, so now let's rework the problem, but let me choose a different location for the exit loss, or for the exit point, point 2. Let me start still at point 1, and then let's draw a different streamline, but this time let's choose one that just goes out this way. Let's call that point 2 prime. So I'm not going to the free surface, but I'm going far away from the end of the pipe out into the region of the fluid where the fluid is stagnant. Okay, so we don't have any movement of the fluid or anything like that. Okay, so let's go ahead and try that point. So let me write out that extended Bernoulli equation. Well, it'll still be the same extended Bernoulli equation. I won't rewrite that, but let me go ahead and write out what the various terms are here. So P1 is still atmospheric pressure. P2 will be a hydrostatic pressure. Density times gravity times whatever this depth is here. Let me just put a depth of, let's call it L, down to that point. V1 will still be 0 because it's a free surface of a large tank. And V2 will also be about 0 because I'm choosing that point 2. Oh, this is 2 prime, I should say. These are both 2 prime. 2.2 prime is about equal to 0 because I'm choosing a point far enough away where the flow basically comes to rest. So it's static. You can see that the pressure here I used was a hydrostatic pressure because I'm assuming that the velocity is basically 0 there. So that's consistent with that assumption. And then we have Z1 minus Z2 prime, our elevation difference. That'll be, if I look at the picture here, that difference will be H plus L. Okay, because now we have a different elevation. And when I substitute back into the extended Bernoulli equation, I'll have H plus L is equal, let me keep that here. So let me, again, kind of think through the algebra here. Before I do that, actually, one thing I should be careful of is when I wrote out P1 and P2 prime. P2 prime I wrote in terms of a gauge pressure. You notice I don't have an atmospheric pressure there. So that was a gauge pressure. So I need to keep P1 as a gauge pressure. So that's 0 gauge. Just to make sure I'm consistent that they're both gauge pressures. Okay, so now let me get back to what I'm working on. So I'm going to bring Z2 to the right-hand side. So I'll have Z1 minus Z2, and that's this term. And I'll bring the P2 prime over to the right-hand side as well. So that'll give me the minus rho GL all over rho G. And then I'll bring the HL term to the left-hand side. And so that'll still look exactly the same as before. And I still have the same exit loss in that case because I'm still going through the exit here. It's no problem. So you can see I have this 0.2 prime, but now you'll notice that this term will cancel out with that term, and I'll be left with the same expression that I had up here. So it comes out to be the same result. I just wanted to show you you'll get the same result even though I chose 0.2 prime in a different location. But I had to make sure that I chose 0.2 prime where I know the velocity and I know the pressure well. Okay, so the only places I really know the velocity and pressure well are either at the free surface here or a point far enough away where the the velocity basically is stagnant, and so I have hydrostatic pressure there. Now, if I chose my point, let me choose a third point. Let me choose point 1 here, and there's some streamline. And let me just end it right there. We'll call that point 2 double prime. And if I applied my extended Bernoulli equation to that point, I start running into problems. And the reason I run into problems there is, if let's say right at the end of the pipe, the velocity there, V2 double prime, would be the velocity in the pipe, right? But the problem is I don't know the pressure there very well. It's not hydrostatic pressure because it's not static, right? It's not a static pressure. So I don't really know the pressure at that point very well. So that point 2 double prime isn't a good point because I don't know the pressure well. I know the velocity, it's just the velocity in the pipe, but I don't know the pressure very well there. I'd have to actually kind of derive it to figure it out, but it's not a good point to use. You're much better off using this point 2, which is what I would typically use, or this point 2 prime. Okay. Okay, let's consider another example. This one, I'm going to draw a tank that looks like this. We have a pipe, free surface here, and I'm going to let the fluid discharge. So this is now out into the atmosphere. Okay, so the end of the pipe ends right here. There's the pipe. So now I'm going to do my extended Bernoulli equation from point 1 all the way, let me go to here, point 2. And in that case, when I write out the extended Bernoulli equation, it'll look like the following. Sorry, it's crammed into the side there. Let's just say that the height here is capital H down to that point. So P1 and P2 are both atmospheric. Point 1, of course, is on the free surface here. Point 2 is as a free jet, so it's out into the atmosphere, so that's why that's atmospheric. V1 is about 0 because it's the surface of a large tank. It's moving very slowly. V2 will be the velocity in the pipe, the average velocity in the pipe. Z1 minus Z2 will be our capital H here for the height difference. HS will be 0 because there's no pump or turbine or anything like that, no fluid machinery in between points 1 and 2. And our head loss term, this is the part that I really want to focus on, we'll have our entrance loss times the velocity head where that loss occurs, plus we'll have a major loss in the pipe times the velocity head in the pipe. Now in this case, there is no exit loss. Okay, so this part gets a little confusing. In the previous example, we had an exit loss that occurred here because point 2 or point 2 prime, we actually passed through the exit and we dissipated all that energy. Okay, the key there is that, we have some velocity coming out of the pipe right at point 2 double prime. That's the pipe velocity. But by the time we get to point 2 or 2 prime, all that velocity is gone. Okay, so we've dissipated all that kinetic energy, and that's why we have that exit loss. But if we stop right at point 2 double prime, or down here at point 2, if we stop right at the exit, if we're right at the exit of the pipe, here we haven't dissipated any of that velocity. So there is no exit loss at this point. So our head loss term will just be what I've written there. There's only an entrance loss, and there's just a major loss. We have no exit loss. Even though we've come out of this pipe, there is no exit loss there because we haven't dissipated that kinetic energy in the fluid. Okay, and even if we chose another point, continued further down here, point 2 prime down here, we still wouldn't have an exit loss because we haven't dissipated that energy. So there's no exit loss in that case either. Okay, if you're going to use point 2 prime, you'd have to figure out what elevation you're dealing with there. It'd still be atmospheric pressure. In that case, your velocity at point 2 prime would actually be different than the pipe velocity, and that's because it's accelerating under the action of gravity now as it comes out of the tank. So just pay special attention when you are calculating exit losses, just to make sure that, if you're going to put that exit loss coefficient, just pay attention to what's happening to the kinetic energy in the fluid. whether you're dissipating it or not. Okay. Now the second item I wanted to comment on concerns equivalent lengths of pipe. Now we've talked previously about using loss coefficients to express the losses in various devices. It's just the pressure difference across the device divided by the dynamic pressure, typically leading into the device or maybe out, exiting the device, but some characteristic dynamic pressure for the device. So for example, we said that if there's a valve and we measure the pressure difference across the valve, flows going that way, we measure that pressure difference, we made it dimensionless using the dynamic pressure, using this expression, and we could get a loss coefficient for that valve. Okay, that's a pretty common way of doing things. There's an older way of expressing these loss coefficients for minor losses, and that's in terms of an equivalent length of pipe. And the idea is this: the loss coefficient is a friction factor times an equivalent length of pipe divided by the pipe diameter. Conceptually, what's happening here is we have some pipe that's leading into this valve, right? So there's some pipe further upstream. Let me just kind of draw that. So you have some pipe leading further upstream, and it has some friction factor associated with it and some diameter, right? Well, let's imagine replacing that valve by an equivalent length of pipe. So let's imagine we now replace that valve by some pipe with some equivalent length such that, let me finish drawing this picture, such that the pressure difference across that equivalent length is the same delta P. Okay, so the idea is I'm going to take that valve out. We're pretending we'll take that valve out and we'll put in some equivalent length of pipe with the same friction factor and diameter such that we get the same change in pressure. We get a major loss that gives us the same pressure difference as the actual minor loss. And we call that the equivalent length of pipe. So sometimes you'll see minor loss coefficients given in terms of equivalent lengths of pipe. And the way to find the K value for that is you just take the friction factor of the pipe leading into it, same with the diameter, and then use that equivalent length in this manner so that the loss coefficient using the equivalent length of pipe would be the same as the loss coefficient if that you would get if you actually had the real device there. So that's called an equivalent length of pipe. Again, it's kind of an older way of expressing losses. Okay, now let's come to the last topic I wanted to cover, and that's the concept of a hydraulic diameter. So far we've been talking about pipes with circular cross-section, but in many cases there are pipes with other kinds of cross-section. If you think about HVAC systems, so heating, ventilation, and air conditioning systems, if you think about those, they often have rectangular cross-section ducts. So we're going to introduce this idea of a hydraulic diameter that allows us to still use our Moody plot and such in the analysis of those kinds of pipes with non-circular cross-sections. So the idea is this: if you look at your screen, we'll define what's known as a hydraulic diameter. It's defined as 4 times the cross-sectional area of the pipe or duct divided by the wetted perimeter of the duct. So the wetted perimeter is just the perimeter of the duct that comes into contact with the fluid. And so that's the definition of the hydraulic diameter. So if you're dealing with the circular cross-section duct with the diameter d, then the area would be pi over 4 d squared. The wetted perimeter would just be the circumference, which would be pi times d. And so the hydraulic diameter would be 4 times the area divided by the wetted perimeter. You'll see that the 4's cancel out, the pi's cancel out, and one of the d's cancel out, and you're left with just the diameter. So the hydraulic diameter just simplifies back down to the regular diameter. Let's just go ahead and do a square cross-section duct, just so you can see how it's applied to something that's non-circular. So let's say this is square with a side length L. In that case, the cross-sectional area will be L squared. The wetted perimeter will just be the perimeter of the duct, which would be 4 times L. So then we plug that into the hydraulic diameter. It'll be 4 times L squared divided by 4L. And so it just comes out to be the side length. The hydraulic diameter is just the side length L. So again, we can use this idea of hydraulic diameter everywhere we had a diameter in our extended Bernoulli equation analysis. So we use it when we look up, when we calculate the Reynolds number and look up the friction factor with the relative roughness. And it works pretty well as long as the aspect ratio of the duct isn't too extreme. It won't work very well if you have like a rectangular duct that's really thin and long. Then you start getting what are known as secondary flows in there, and it doesn't, the correlations don't work very well in that case. But as long as you have an aspect ratio that's not too extreme, maybe an aspect ratio greater than 3 or 4, something like that, then we can use this concept of the hydraulic diameter and still use our extended Bernoulli equation in the Moody chart and everything, just like you would for a circular duct. Now, if you're dealing with partially filled channels, like, for example, what's called open channel flow, let's say a duct where you have fluid just kind of partially filling it, then there's another concept called a hydraulic radius. And it's really kind of outside the scope of what we're going to do in this course. It's kind of like a hydraulic diameter, but a little different. So we're not going to get into that here. But partially filled ducts are very common in civil engineering applications. But if you want to learn more about that, then you need to go outside this course. All right. I think that we've covered everything for today. What we'll do in the next lecture is we'll talk about different kinds of pipe systems that we encounter and what some of the unknowns are and how we go about solving them. So that'll be for the next lecture.